Welcome to SanfordFlipMath. This is AP Calculus. We are continuing to work through the book put out by Finney, Demana, Kennedy, and we are deep in the throes of section 5.3, which is really about the rules for integrals, and now we're kind of drifting into antiderivatives and how they relate to integrals. One loose end I want to tie up is the mean value theorem for integrals. We started talking about conceptually what that meant, and I just wanted to kind of clarify again that the basis of what it is, and then do an example with it, and then we will talk about antiderivatives. So this part I'm not going to spend a lot of time on. It says sketch. Now you need to know that it is very likely to have a question that's similar to this on a test or a quiz or something like that. Sketch and explain the meaning of the mean value theorem for integration or for integrals or for definite integrals. And this is the mean value theorem for definite integrals, and let's illustrate what it is about. Okay, so first of all, it is about the average value or average value of the function on a closed interval. And so like we could be going from A to B, let's say. And if I'm illustrating what the average is, basically if you find this area and you wanted to know, you know what, if this really was a rectangle, what would that rectangle look like? It would look something like this, and it would have a height that's the average. So what we're saying is, again, if I look at the area from A to B, the integral from A to B of f of x, and know that if I make that equal to the area of a rectangle, okay, so, and the rectangle would be something like width or base, sorry, it would have been b minus a, times some height. Well, that height is the average height. And then if I divide both sides by the b minus a, that becomes this. Okay? That's what it becomes. Now, at some point on this thing, based on the way I drew it, at some point on this thing, this height is going to be equal to the height to the curve itself. And notice this is the spot where they intersect. So that x value is c. That's the x value where the average f is equal to f of x. That's what that is. So here it is, the average equals f of x. Okay? That's all I want to say about that. This is really a recap of the ideas, the last ideas in the last section. Okay, I want to do an example about this. And this looks kind of scary, but it's really not that bad. What it says is find the average value of the function. And you're specifically told to use geometry. And I'll give you a hint. This little guy here has something to do with a circle. Okay, and if we do a little graph of this thing, you can type it in the calculator if you wish. It's going to look something like this. This is 1. And so what we're really looking at is it would have been a circle at x squared plus y minus 1 squared equals 1. So this is a circle of radius 1 centered at 0, 1. And then if you solve this thing for y, that's what comes out of this. Okay. And this is actually the bottom half. When you do the plus or minus, this would be the minus half. And it says find the average value of the function. Now what that means is if I find the area from here to here, the average height would be the height of an equivalent rectangle that gives us the same area as that red area. Okay, so the idea is this blue area and that red area are the same area. And if it would have just been a rectangle, it would have the same area, and the average height is that y value. Okay, so again, that's just an illustration, and you might be asked to illustrate it on top of a problem like this. Okay, all right, so I'm going to get rid of that. Oop, put that back. Okay, all right, so we're going to do the average value. So we're going to do the integral from -1 to 1 of this thing, dx. And to make it an average value, we're going to divide by the width of that interval. And that's it. Now, it says use geometry because we don't really have the algebraic techniques or the calculus techniques to do this. This is calculus in terms of concept, but it's not calculus in terms of we're not going to add up a bunch of rectangles and we're not going to pick a limit and all that kind of stuff. So what I need you to picture is, here's a circle. This would be half that circle. The red stuff on the outside comes from a rectangle minus the semicircle. Well, the rectangle from -1 to 1 would be too wide by a height of 1 minus, so the area of the entire circle would be pi times the radius squared, but it's only half of it because it's a semicircle. So that area is going to equal 2 minus half of pi. So that, what we just found, was the red area. That is this area. Okay, how color coordinated is that? So now what I'm going to do is the average value of f is equal to 1 over 1 minus -1, b minus a, times what we just said was that area. So half of 2 minus pi over 2. I will tell you that if we're calling this part A of the problem, then this is the answer to part A. If we were supposed to round it, then we would type that bad boy in the calculator, and we would get 0.4292 bunch of stuff. So if you're saying 3 decimal places, then here it is. Okay. All right. So that is part A, or the first part of this question. Now the second part of the question says find C for the mean value theorem for integration. Well, the mean value theorem for integration says there is a spot where the function is equal to that average. Well, the function was this ugly equation, 1 minus square root of. Okay, so it says there is a spot somewhere. Oh, that was nice. Okay, let me erase that. Sorry. Hit a button somehow. There is a spot where the function, f of c, that's the spot where the function is equal to the average. That's what the mean value theorem says. Mean value theorem. So I'm going to take the function and make it equal to the average. Okay, now just understand that the numbers I'm working from here are really coming from the stuff that's already in the calculator. Okay, all right, and I'm going to solve this and then we're done. Okay, so I'm going to -1. This is just a bunch of algebra now. Okay, -0.57-ish. Divide both sides by the negative. Well, it doesn't really matter. We're going to square both sides anyway, but I'm going to go ahead and write it. Okay, so I divided both sides by a negative. Now I have to square both sides to get rid of the square root. So 1 minus x squared equals 0.32. Okay. Now again, my goal is to find x, and I know I'm kind of moving along here, but this is just the algebra part, so this isn't even calculus anymore. I know that's hard to swallow. Sorry. 0.674-ish. Again, divide both sides by a negative, because now I need to take a square root. Okay, I'm going to get a little picky here on notation now. Ultimately, it needs to be a plus or minus. I just want to remind you that square roots technically are not negative. So when I do the square root of x squared, this is really absolute value of x equals, when I type this square root in, I get 0.674. No, I did that part already, 0.82. And this is where the plus or minus comes in, because if the absolute value is positive, then I could have had the absolute value of a positive or a negative. Now, I guess my question is, does it make sense that there are two x values? By the way, this is the c value. Does this make sense that there are two x values where that average happened? So 0.8-ish is the x value. I'm going to come back up to the graph. So we're really talking about like here, and notice that's where my rectangle would really be. Okay, that's where my rectangle for the average would be. Okay, all right, enough about that. You can watch that 100 times if you wish. I need to talk about a convoluted argument. Okay, so let's change gears for a second. We've been talking about what integrals mean. And now we need to make the supreme connection in all of calculus. So imagine yourself, you've been Leibniz all this time playing around with differential calculus, and then you bump into Newton, who's been working on integral calculus all this time, and you start having a conversation. So this is Newton and Leibniz having a conversation about calculus. So they're discussing this whole relationship between area and velocity. And if you recall from the beginning of this section, this chapter, the area under a velocity time curve is distance. So the area under a velocity time curve is distance because it's velocity versus time. And when you multiply them, it's basically velocity times time, which is distance, and that's no big stretch. Okay. Well, we've been saying integral is area. And because of this, we're basically establishing vocabulary at that point. So integral is distance. Okay, now popping back to chapter 3 when we were talking about derivatives, the derivative of distance is velocity. Okay, now this is going to feel convoluted. What I'm going to want you to do is I'm going to talk through this, and I'm going to want you to back up and hear it again or pause it and talk yourself through it again. Okay, so integral is distance. End of that issue. Well, the derivative of distance is velocity. So the derivative of distance is velocity. That means the derivative of area is velocity, since area is distance, since integral is distance. So the derivative of integral is velocity. I know this sounds dizzying. It sounds circular. Okay, so this is the big deal. So if the derivative of area is velocity, then when I undo the derivative of velocity, I get area. Undo the derivative. If I undo the derivative of area, I should get back to distance. So undoing the derivative of velocity, undoing the derivative is distance, then antiderivative ends up being area. Now see, I've talked myself out of it. I'm almost confusing myself. You need to go through this again. Ultimately, this is the capper for it all. Antiderivative is integral. That doesn't sound very deep, but to the two people, Leibniz and Newton, who were working on this from completely different ends, they were like amazed. So the basic deal is, if I undo derivative, I find area. I do derivative, I find slope. If I undo slope, I'm back to distance, but I'm also finding area. Area and distance are the same. It's all interconnected. So what are we going to do now? We're going to find integrals by doing antiderivatives. So for instance, if I was just going to do the integral from -2 to 3, I would start at -2, go to 3. I'm doing of 5. So this is what y equals 5 looks like. And I would do this integral by just going up here up here. Wow, this is a rectangle. That's so exciting. Thank you so much. That distance is 5. Distance is 5. Area equals 25. I'm telling you, if you do the antiderivative of 5, it had to be 5x. Antiderivative of 5 is 5x. So in other words, if I do the derivative of 5x, I get the 5 back. And then I'm going to evaluate that from -2 to 3. Now, what does that look like? Well, what we're going to do is substitute the 3 in, minus substitute the -2 in. So this becomes 15 minus -10, which is 25. Now, you might be saying to yourself, so that looked like a lot of work to do 5 times 5. Okay, I agree with you. But what does that look like? Okay, I need to do some erasing, so if you need to, hit pause real quick if you need to write this down. Okay, so if I need to do the antiderivative, find the area, find the integral of 3x squared from -1 to 2, well, suddenly this is a little more work. Okay, suddenly this is starting to look like, okay, this is -1 to 2. This is now starting to look like a bunch of rectangles, and then how precise can I be in doing those rectangles? So I'm telling you, we can do the antiderivative of 3x squared, which would be x cubed. It would be 3x cubed over 3, which is x cubed. Now, if you're saying to yourself, where's the plus c? That is a really good question. There should be a plus c. But what I'm going to tell you is, because we subtract, we'll have a plus c and then a minus c. They end up canceling out, so it doesn't matter. Okay, so we're going to evaluate this at -1 and at 2, and we're going to subtract. It's always the one from the top minus the one from the bottom. So this becomes 8 minus -1, also known as 9. So the area between -1 and 2 under 3x squared is 9. Guess I needed myself a little bit more room. All right, cooking right along here. In fact, let's make some more room. Sneaky, Mr. Sanford. Oh, that was funny. Sneaky, but not so helpful. All right, let's try again. All right, so I'm saying I want the area under the cosine curve. Now the cosine curve looks like this. This would be pi. This would be pi over 2. Okay, so I want the area between 0 and pi over 2. Well, to do that, I'm going to do antiderivative. The antiderivative of cosine would be sine plus c, but again, the c's are going to cancel out when I subtract. So sine of x, I'm going to evaluate that between 0 and pi over 2. So that means I'm going to do the sine of pi over 2 minus the sine of 0. So this is 1 minus 0, which is 1. Isn't that bizarre? The area of this ugly little curvy, funky thing is 1. I think that's kind of sweet. All right, one more of this, and then we're going to cut you loose. All right. I want the area of 1 over 1 minus x squared between 0 and 1/2. Well, what the heck does that look like? Well, just graphing it actually, I just did this in the calculator. It looks kind of like this, and it stops, which really should make sense if you think about, if you put in 1 here, 1 makes this undefined, and anything bigger than 1 would make it the square root of a negative, so that's imaginary. So if I'm doing from 0 to 1/2, okay, so this is at 1, 0 to 1/2 would be like right here. Okay, so I want that area. Okay, so how do we do this? Well, we'll do antiderivative. Well, antiderivative of this, now this is kind of scary looking, but this is actually inverse sine. We're going to evaluate that between 0 and 1/2. Now this is going to pull things up from pre-calc. Inverse sine means what was the angle? So I'm going to do inverse sine of 1/2 minus inverse sine of 0. Well, what was the angle to give me a sine of 1/2? Well, this is a unit circle thing. This is actually, so the y value is 1/2. This would have been square root of 3 over 2. This is a 30-degree angle, so I'm going to call this pi over 6. And sine of what gives me 0? Well, that's at 1, 0, so that was a 0-degree angle. So the answer to this is pi over 6. So this little area right here is pi over 6. All right, well, this gets us started with antiderivatives, our integrals. Okay, just one little point of clarification. When we did this antiderivative, we did inverse sine of x. We will talk about this at some point, but if I have this, this is going to look the same, but you need to know that this is technically not the same since there are no limits here. This just means do the antiderivative now, since they end up being virtually interchangeable. So this would be inverse sine of x plus c. So this is where the c comes in. If there are no limits, then you need the plus c. All right, and we're going to leave it at that. Thank you very much, and we'll see you in the class. Bye.